Here I am with my new hairstyle.
Oh, did you get a haircut?
I did. My vapor pressure is really important. And if you just saw on that little quiz that we had, I showed you a graph. And what's important to understand is no matter what substance it is, let's say this is 760 millimeters of mercury. And I showed you different curves, and this was temperature. And we saw these curves that look like this. And the definition the definition of boiling point is when a substance's vapor pressure, it's the temperature at which the substance's vapor pressure equals atmospheric pressure. Okay, let's keep that in mind for a little bit. But notice these curves, they kind of look like exponential curves. And we're going to see an equation tomorrow that deals with that. But one of the things to think about is, let's say, for example, I think on the quiz we had pentane. I don't remember exactly.
Oh, tetra, pentane. What's
Pen,
the next one?
pentane and whatever. Maybe this was. Oh, I have it right here. I can look. Let me take a look here.
Maybe it's
Tetrachloromethane, which is a cool looking molecule, very very heavy, and then I think finally was water. And so notice how, and Anna brought up a good point. How can we tell which is the highest vapor pressure? Well, go to any temperature. Let's say, if this was 20 degrees, maybe this was 30 degrees. It doesn't matter. You just take just look up here, and obviously the vapor pressure is lower for water than it is for tetrachloromethane, than it is for pentane. Now, the question becomes, why is that the case? And if you were to look at these molecules, there are a couple of competing factors here. I shouldn't say competing factors, I should say contributing factors. And we have molecular polarity. And we talked about polarity of molecules, and I showed you some examples. For example, like H2O. And we learned that H2O was very, very polar. And polar, once again, meant we had a charge separation, and that delta means partial charges. And we were able to represent that by saying, hey, I have something called the dipole moment, which is just a fancy word for saying, here, that part of it is more positive and more negative. So we represent it by a vector, and a vector is something that has magnitude and direction. When you study physics next year, vectors are going to be the big deal here. There. So very polar molecules are attracted to each other because of charge separation. We have sort of an electrostatic, negative attracts positive and positive attracts negative. So oxygen is very electronegative. As a matter of fact, the three most electronegative elements on the periodic table are nitrogen, fluorine, oxygen rather, and fluorine. So if you see molecules that contain oxygen, for example, if I've got CH, oh, my handwriting is terrible today. If I have CH3 OH, this is methyl alcohol. If we were to take a look at its structure, it would have a structure like this. A C, now remember our VSEPR, up, 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 and this would be HHH. So again, this is not a very polar part. These alkyl groups, alkyl are just carbon and hydrogens, sp3 hybridized carbon. They're not very polar. Of course, down here, this is not very electronegative, but oxygen is very electronegative. So it's going to have a dipole, again, in that direction. Now, it's not going to be as great a magnitude as water, but still in all, this has a boiling point somewhere around 70-ish degrees, 73 degrees Celsius. Water has a boiling point of 100 degrees. Let's take a look at a molecule that's very similar to to water, and that's H2S. Same shape. Same geometrical shape. Sulfur is in the same column, the same group as oxygen, but it's much less electronegative. As a matter of fact, this is a boiling point of 100 degrees at room temperature, or at normal atmospheric conditions. This is a gas. So the stronger the bond polarity, the higher the boiling point, and the lower the vapor pressure. Now, let's take a look at some other molecules, like pentane, that one that had a very high vapor pressure. Okay, so polarity, that was one thing. And we would say that it has what are called dipole, maybe you should jot this down here, dipole interaction or attractions. So if I have highly polar molecules, the vapor pressure will be lower, the boiling point will be higher because of the fact that they are strongly attracted to each other. Okay, let's take a look at the next thing would be nonpolar molecules. And they're kind of interesting because we can have nonpolar molecules that have incredibly low boiling points and incredibly high vapor pressure. Pentane was an example. Pentane, 1, 2, 3, 4, 5. That was our shorthand notation for it. But really it's CH3, CH2, CH2, 1, 2, 3, CH2, CH3. And it's not a very big molecule. If you calculate the molar mass of it, 1, 2, 3, 4, 5. So it's C5H12. So we have 72 grams per mole. Not a very large molecule. And it's very, very volatile. Very high vapor pressure, very low boiling point. Why? It's nonpolar. We don't really have that much intermolecular forces of attraction to it. But let's take a look at some other molecules. Well, let's stick with these. Now, first of all, let me give you a little bit of nomenclature here. I'm going to be talking about these types of molecules for a little bit, where every carbon is sp3 hybridized. In other words, every carbon has that tetrahedral arrangement, and we're just going to look at hydrocarbons. Now, hydrocarbons just have carbon and hydrogen, and these are called alkanes. Alkanes. When I first came here to Elk Lake, there was a gym teacher named Al Kanes, and I always kind of laughed because that made me think of these molecules. They're nonpolar molecules. So as a matter of fact, if you took something like, any one of these molecules, pentane's a liquid at room temperature. If we put it in water, they'd separate out because water's polar and this is nonpolar. And in order for things to be soluble, you have to have like dissolves like. I can have polar solvent dissolving polar solute. So for example, if I took water, I could dissolve some sugar in that because sugar is a polar molecule. Glucose is a polar molecule. And something that would dissolve a nonpolar molecule would be other nonpolar molecules. But let's take a look. That's pentane. But if I just go down one carbon, the butane, 1, 2, 3, 4, and again, you could fill in all the hydrogens, or even propane. Notice these are still hydrocarbons, CH3, CH2, CH2, CH3, etc. These are gases at room temperature. So there are two things playing here. There's like, well, this is a liquid. These are gases. So we have some intermolecular forces of attraction. But we're going to have to think about those. In this case, are some molecules gases and some liquid? And I could go up, let's say now I have a molecule, and I just keep making this chain of carbons longer. I have something like decane. Has 10 carbons. It's C10H22. And you might say, hey, Koch, how do you know these formulas off the top of your head? Well, if you remember back in the old days, we talked about like hexane. We gave these metric prefixes. So we had mono, di, tri, uh, tetra, etc., etc. Penta, hexa, hepta, octa, nona, and deca. And these were our prefixes. This meant 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after we get through the first few of these molecules, we start using these prefixes to name these things. So pentane has 5 carbons, and hexane would have 6 carbons. And the way you write formulas for alkanes is I have C N H 2N plus 2. So whatever your number of carbons are, you just multiply that by 2 and add 2, and that's going to give you the number of hydrogens. So I could come up with decane, C10H22. So that's how you know those formulas and those names of those formulas. So anyone have a phone or you have your Chromebook? Can you look up the boiling point of decane?
$74.
174 degrees C, right? Or point, whatever. It doesn't matter. But the point is that it's a nonpolar molecule with a boiling point almost twice that of water. So what's going on here? What's going on? We don't have any polar intermolecular forces of attraction. There's something going on called London dispersion forces, aka van der Waals forces. Okay. So we have two things here going on. Nonpolar molecules could be gas at room temperature if they're tiny. Size matters though. The larger the molar mass, the more you have stronger intermolecular forces of attraction. The question becomes, well, why is that the case? So I'm gonna illustrate that not by using these alkanes, although we can think about this a little bit later, but just by using some diatomic halogens. Okay. If I have fluorine gas, F2, it's about 38 grams per mole. And fluorine, if you were to draw this, you could draw it like this. And fluorine, very tiny atoms. So when they get together, this molecule is pretty light. And not only is it light, it's tiny. Okay. If I were to draw the electron distribution around this is going to keep the electron cloud that surrounds the sigma bond here pretty tight. Not very flexible, for lack of a better term. But as we move down here, well, chlorine is about the same. Chlorine, it's got its electron cloud, a little bit bigger, but still a gas at room temperature. Now you have to picture in your mind that the distribution of the electrons around a diatomic molecule in this case, it's not like a perfect football. The electrons are going to sometimes be more over here, more over here. It's sort of like taking a balloon and squeezing it and have the air go up that side and that side. Now, it's harder to do for these smaller molecules, but when we get to something like bromine, it's got a pretty big, these are big atoms, and it's got a big electron cloud around it, if you will. The electrons are distributed in such a way that it's quite large. So you could have, well, maybe more of the electrons congregate over here at one point. And that gives this kind of a induced positive charge, induced negative charge. Matter of fact, this is called an induced, well, hang on. Let's get to induced next time because we're running out of time. The idea is this is a liquid at room temperature. Okay? Why? Because I can have the electron cloud sort of asymmetrically distributed, and the next BR2, well, if there are more electrons over here, it's going to push the electrons kind of away here and get a little bit more of a positive feeling on that side. This is called an dipole, or this is called an induced dipole type of an attraction. By the time we get to I2, iodine, this is like a huge, well, it's a little bit exaggerated, but it's a huge electron cloud around this if you think of it that way. And so this is very, very malleable, or very, very fluxional, and you can have your charges congregating over here, negative charges, and a more positive field on that side, and it gets to the point where that combination of the electrons around the iodine and its molar mass go into making this a solid. So don't think that nonpolar molecules are always going to be gases, or they can be liquids, they can be solids. If we went with our old alkanes and I just kept going like this, before you know it, you have solids that are just nonpolar solids. So I'll pick up with that tomorrow. We'll talk a little bit more about intermolecular forces of attraction, and I think you'll enjoy it. It's very intuitive stuff. Right, Julie? It looks sad.